theoretical notations. O is a discrete valuation ring with quotient field capital K and uniformizer Z. G is an almost simple split, simply connected Chevalier group scheme over Z. We'll fix a pinning TBG over Z. Let phi be the root system of G relative to the pinning. So for every root R in phi, let UR denote the corresponding root group. So this is the these are the notations that I will need for the first 7 slides, and these are standard. And let omega alpha check denote the covariate corresponding to a simple root alpha. This we'll need later. And to summarize, our context is the most geometric. Now I'll recall some basic notions of Bruhat-Tits group schemes. Let YT denote the group of 1 parameter subgroups of the maximal torus T. Let AT be YT tensor R. This is the apartment of T, and implicitly the origin of the apartment has also got fixed. So now definition, a subgroup Q of GK is called schematic if there exists a smooth group scheme, O group scheme G with connected fibers and a finite type with generic fiber isomorphic to G cross spec K and whose O valued points is Q. Now I want to motivate what we will call bounded subgroups of GK, and we'll do it slowly. We are interested in subgroups Q of GK with valuation bounded below uniformly. This can be made precise by taking a faithful representation of G. So we can think of our group as a matrix group, and then it's a very simple-minded thinking about the entries, the matrix entries and their valuations. Let us extract an attribute of such subgroups. So here's a remark: for a root R in let FR be the minimum valuation as we vary over elements in the big cell of Q. We now make an observation. It's a very simple observation. Suppose R1 and R2 are roots such that R1 plus R2 is also a root. Then we have the obvious inequality. F of R1 plus R2 is less than equal to FR1 plus FR2, which means that the minimum valuation as we vary over elements in the big cell of Q at R1 plus R2 is bounded above by FR1 plus FR2. So here is a one-line explanation for this. Indeed, if little q1 and little q2 have valuations little v1 and little v2 at R1 and R2 respectively, then the valuation of the product q1, q2 at R1 plus R2 is bounded above by v1 plus v2. If you want, you can think about just matrix multiplication, and this observation follows immediately. This observation motivates the following notion: set phi bar as phi union 0. Definition: a function f on phi bar taking values in the real line union infinity is said to be concave if for all roots R1 and R2 in phi bar, such that R1 plus R2 is also in phi bar, we have FR1 plus R2 is less than or equal to FR1 plus FR. So we have just formalized this observation. Thus, we see that bounded subgroups of GK lead to concave functions. Some obvious examples are functions taking a constant positive value and restrictions of linear functionals on the apartment. Some obvious operations on them are taking sums of concave functions, ceiling functions of concave functions. That is, if we start with a concave function f, consider the association R goes to ceiling of f of R. This is an elementary check that this is also a concave function. And taking supremum of a set of concave functions. Now, I wish to discuss some assumptions. And the point is that without loss of generality, they will allow for a simplicity of exposition. And without them, the exposition will be technical. The return on investment will be very less. In this lecture, for simplicity, we will only consider concave functions satisfying f0 equals 0 and taking values in R instead of R union infinity. We'll see later why I'm doing this. But henceforth, we will assume that our bounded subgroups always contain O-valued points of the maximal torus T and have a non-trivial intersection with the root group URK for every root R in phi. So this is what I want. This will avoid degenerate cases of bounded subgroups of GK. For instance, we want to avoid some SL2 sitting in SL3 thought of as a bounded subgroup. Yeah, so these assumptions and their analogues will be vogue throughout the lecture from now on. And I need them for the simplicity of exposition. So now I want to discuss some important examples of concave functions. The first, we want to call them as type 1. So for any point theta in the apartment and any root R in phi bar, we set mr theta as the ceiling function of minus of r theta. So notice that when R is 0 in phi bar, then 0 evaluated at theta is 0. So we are getting m0 theta is 0, which is part of our assumptions. The second example is type 2. So more generally, for a bounded subset omega in the affine apartment AT and a root R in phi bar, set mr omega as the ceiling function of the negative of the infimum of r theta as theta varies in omega. Notice again that when R is the origin, R is 0, then mr omega takes values, which is in agreement with our assumption. Not every concave function arises from a bounded region. And we have examples over G2. However, for groups of AN type, every concave function comes from a bounded region. And this observation will be useful later. So now I want to remind you a little bit about classical Bruhat-Tits theory. In the simplest case, namely the split case, we have seen that bounded subgroups of GK give concave functions, give rise to concave functions. Bruhat-Tits turn this around as follows. To a concave function f, we may associate a bounded subgroup of GK as follows. This is a subgroup of GK generated by O-valued points of the maximal torus T, and for every root R, the root group has almost O-valued points, except that the uniformizer Z must have a zero of order at least FR. To summarize, we have two constructions. From bounded subgroups of GK, we have seen how they give rise to concave functions. And from concave functions, we have a construction of bounded subgroups of GK. Thus, concave functions determine the most general class of bounded subgroups. Now, I want to recall to you a theorem of Bruhat-Tits on group schemes. For each concave function f, there exists a smooth group scheme G subscript little f on spec O with connected fibers whose generic fiber is isomorphic to G cross spec K, and the O-valued points GF of O equals the bounded subgroup PF defined above in GK. When F arises from a point in the apartment AT, then the corresponding groups are called parahoric. That is of type 1 in our terminology of type 1. Here I'm just trying to habituate you to our terminology of type 1 and type 2. So now I'll begin my lecture on higher dimensions. I have to set some notations and also some basic notions. So now O is a DVR with the residue field of large characteristic. Let On be the power series ring in n variables over O. And it would be convenient to denote the uniformizer of O by Z0. Let Kn be the fraction field of On. We are interested in bounded subgroups of GKN. What do we mean by them? That is containing the On valued points of T and having a non-trivial intersection with the subgroup URKN of GKN and of valuation in each uniformizer Zi bounded below uniformly. Thus, for each uniformizer, we get a concave function on phi bar with values in R satisfying F0 is equal to 0. Inspired by Bruhat-Tits, we turn this around. It is this extraction of concave for every uniformizer, the extraction of a concave function. So definition, let I vary between 0 and n. And we suppose that we are given concave functions fi. Define the n+1 concave function boldface f as the n-uple, n+1 uple, taking values in Rn+1. To boldface f, we can associate a n+1 bounded subgroup of GKN as follows. It is a subgroup of GKN generated by ON valued points of the maximal torus T. And for every root R in Phi, the root group UR has almost ON valued points, except that we demand that each uniformizer Zi must have a zero of order at least Fi of R. So here I have introduced bounded subgroups of GKN, and the notation is P subscript boldface F. Thus, PF over ON is a direct generalization of PFI over the DVRs, which are the localization of ON and the prime ideals generated by Zi. It is the most general class of bounded subgroups of GKN. Definition: we call a subgroup Q of GKN schematic if there exists a connected, smooth ON group scheme G of finite type with generic fiber isomorphic to G cross spec Kn and whose ON valued points is Q. So this is just a direct generalization of the usual notion of schematic subgroup of GK. So here is a question: is PF schematic? By the theorem of Bruhat-Tits that we discussed a little while ago, the PF for in the case of local fields are schematic. So this question is inspired from there. Let us see a feature of the multiplication law in higher dimensions. So now let's see multiplication law in higher dimension paraphorics. So we take the case G is SL3, and the discrete valuation ring is the power series ring in one variable over the field little k. Thus, O subscript 1 is the power series ring in two variables over little k. Let F0 and F1 be concave functions given by the coveights omega alpha 1 check by 3 and omega alpha 2 check by 3 in the apartment respectively. So this is these are points in the apartment, and therefore they give rise to concave functions by the construction MR theta. That is the type 1 construction. We set boldface F as the pair F0, F1. Now here I'm just recalling the definition of bounded subgroup of GKN. With this definition, in GKN, GK1, we get for our choice of F, the subgroup PF, which will be a 3x3 matrices in SL3 of capital K1, where the Fij's are in the formal power series ring O1, and the main feature is that the 2,1 entry must have a 0 of order at least 1 in Z0. The 3,2 must have an 0 of order at least 1 in Z1, and 3,1 must have a 0 of order at least 1 in both Z0 and Z1. So this is just a consequence of our choice of these points in the apartment. Now let's take two elements, Gij and Hij, in the bounded subgroup P boldface F, and consider their product, which I call Fij. So we see that the 3,1 entry looks like this. If we leave out Z0 and Z1, we have almost the usual product in SL3. And for 2,1 entry, the multiplication looks like this. In other words, the multiplication law for the entry 3,1 is like that of SL301, but that of 2,1 has an extra Z1.
So sorry, this
yes.
P, what you described, they are just the generators of PF. Okay, this is not a set, right?
No, I have just taken two arbitrary elements in.
No, but you wrote, you are writing that PF consists on the element of this with this big 3 by 3 by 3 thing.
Yes. Yeah.
I mean, there are all, no, I mean, they are not all of them. The generators are all of them like that. No? No? You don't see
I think this describes them.
No, but I mean, this is not a bracket. I mean, this is a. You mean PF is generated by those elements, right?
Yes. Yeah.
Okay. Thank you.
Yeah, but the phenomena I want to show, certainly I have elements of this type in my group PF, and then I am saying that take two elements of this type and look at their product, which again is of this type. But what I'm trying to emphasize is that the 2,1 entry has this extra Z1 when we multiply. And similarly, the entries 2,2 and 1,1 are unlike the one-dimensional case. So these are new features that appear in the multiplication law in high-dimensional paraphorics. Now, I want to explain a basic geometric setup and a question. So take the case of polynomial ring in C and eta. The local rings at the generic points of the standard divisor C axis and eta axis are the DVRs, little k round bracket eta, adjoint C, localized at C, and the other one. Their specs are tubular neighborhoods of the axis. So I've given this example just to familiarize you. Let A0 denote the complement of the axis in the affine space A and K. Let U be the union of A0 with the specs of DVRs, which are the local rings at the generic points of the standard divisors in A and K. Thus, the closed subscheme, which is the complement of U, has codimension 2 in A and K. Question: suppose we are given Bruhat-Tits group schemes adapted to the standard divisors of A and K, which means that suppose for the generic point of each of the standard divisors of A and K, we are prescribed Bruhat-Tits group schemes. Using the identity function, we glue them with G cross A0, the trivial group scheme with fiber G, to get a group scheme on U. So now we have a group scheme on U. Does it extend to the whole space A and K? this is the question. More generally, given data on height 1 prime ideals, this extension problem across codimension 2 can be formulated for A and O as well, where O is an arbitrary discrete valuation ring in mixed characteristic, anything. So this is the basic geometric setup and the basic question we have in mind. So we have two questions. One is that whether the bounded subgroup P boldface F is schematic or not. And the second is an extension problem. Now I wish to discuss counterexamples in Bruhat-Tits. And just give the first slide just gives an overview. So these are examples in section 3.2.15. So the base ring is O, which is a polynomial ring in C and eta. So I wanted to stick to Bruhat-Tits notation. So exceptionally in this counterexamples, O is denoted like this. It's no more a DVR. I'm abusing notation here. The group G is SL2. So the root system phi is plus minus A, and the quotient field is little k round bracket C and eta. The Bruhat-Tits group scheme correspond to the concave functions defined by f0 of A is CO, and f0 of minus A is O, and f1 of minus A is eta O, and f1 of A is O. So I have written this just to imitate what Bruhat-Tits have written, but we can write it in our language. Thus, f0 of A is 1, and f0 of minus A is 0, f1 of A is 0, and f1 of minus A is 1. So Bruhat-Tits demonstrate that taking schematic closures in certain linear group schemes, GLM, over the affine plane A to K, could give schemes which are not flat and therefore not group schemes. By discarding certain bad components in the fiber over origin, they extract a group scheme on A2 whose affineness is left in doubt. Let us describe the lattice M, giving the linear group scheme GLM considered by them. Before going ahead, I just want to say that taking schematic closures in certain linear group schemes is a recurring technique in Bruhat-Tits. And this technique is running into problems over already A2K in the simplest case of Chevalier group scheme, split Chevalier group scheme, and SL2. So now I want to give some more details. We call G is SL2, and the field capital K is little k round bracket C and eta. The faithful representation is rho, which is identity cross capital add on the module, which is two copies of capital K, and the Lie algebra of SL2 tensor K, capital. The O module M is a free module generated by elements of this type of G tensor K and the standard basis of K2. So I'm just trying to carry along notations of Bruhat-Tits. So thus we have that if you take an element which looks like little x, little y, little z, little t. So this is an element in capital K valued points of SL2. This goes under the representation rho to something of this type. There's a 2x2 matrix, and then there's a 3x3 matrix, and together they form a 5x5 matrix. And notice that we have taken an inverse here and an inverse here. Let G be the schematic closure of G cross spec K in GLM. Its fiber over the origin is the union G01 union G02, where G01 has dimension 4 and G02 has dimension 3. Hence, G is not flat over O. While H, which is G from which we have taken out G01, is a flat group scheme. But in the words of Bruhat-Tits, mais probablement pas affine. Now, I just want you to remember this notation of H, because it will come 4 slides later on slide 17, after I have discussed our main theorem, which is coming now. And I would also like you to remember this notation of a linear group scheme GLM, where M is the lattice, because it will come much later on slide 23. So now I want to discuss the types. These will serve as bootstrapping structures or structure d'amorçage. Definition: let points theta j in the apartment for j between 1 and n be given. We form from them boldface f subscript theta, which is, let this be the ordered set of concave functions associated to them by the function r goes to mr theta. That is the type 1 technique. These will be called n concave functions of type 1. For j between 1 and n, suppose we are given bounded subsets omega j in the apartment. Let boldface f subscript omega be the ordered set of concave functions associated to them, to these bounded regions omega j, by the association r goes to mr omega. These will be called n concave functions of type 2. Let n arbitrary concave functions fj on phi be given. Let boldface f denote the ordered set formed by them. These will be called n concave functions of type 3. So we'll do a bootstrapping on them. Now I want to state the main theorem. For a n+1 concave function boldface f of each type, there exists a smooth group scheme G subscript boldface f of finite type on A and O with connected fibers, whose generic fiber is isomorphic to G cross spec Kn, and we have an identification of its ON valued points with the bounded subgroup PF that we have seen earlier. That is, the n-bounded subgroup PF is schematic. The group scheme GF is affine when F is of type 1. And in types 2 and 3, it is at least quasi-affine. GF has nice specialization properties when restricted to the diagonal in A2K and more generally. So here I did not want to enter into complications of notations. So I have written like this. But what is the main point? On the diagonal of A2K, the restricted group scheme corresponds to the concave function, which is the sum of the concave functions chosen on the axis. Two BT group schemes arose first in the work of Vikraman Balaji on degenerations of principal G bundles when a family of smooth curves degenerates to a nodal curve. So this is our main theorem. Now I wish to reinterpret the counterexamples of Bruhat-Tits in terms of our types. So we have the root system is plus minus A, and let omega check be the covariate corresponding to A. This slide is mostly elementary. We set theta naught as omega check by 2 and theta 1 as its negative. Thus, the root A evaluated at theta naught is A evaluated at omega check by 2, which is half, and therefore minus A theta naught is minus half. Then since MR theta is the ceiling function, we get that MA theta naught is ceiling of minus half, which is 0, and M minus A theta naught is ceiling of minus half, which is 1. Similarly, for MA theta 1 is 1 and M minus A theta 1 is 0. In other words, for I 0 and 1, we have the previous Fi at A is MA theta I. So we have managed to reinterpret the concave functions Fi of Bruhat-Tits in terms of MR theta I, which are of type 1. So it's a very elementary slide. Now, setting boldface theta as the pair theta naught and theta 1, by the main theorem, the group scheme we get, which is G subscript boldface F theta, is precisely the scheme H. It is also smooth and affine group scheme over A2. Furthermore, the diagonal restriction of G theta is the affine group scheme G, which will denote M theta, given by a very simple concave function, which takes value 1 for every root, and there are only 2 of them, A and minus A. This concave function gives the subgroup P diagonal theta, which is obtained by setting the two uniformizers C and eta as the same as T, and is the concave function considered in 3.2.14 of Bruhat-Tits. Now, here's a very simple observation. Notice that MR theta plus M minus R theta is this sum of two ceiling functions, and it must necessarily belong to the set 0 and 1. Notice that M subscript theta is not of type 1 because M theta A plus M theta minus A is 2. Since this sum is not in 0, 1, so M theta is not parahoric, even though individually the two theta i's are. So I want to show this phenomena because almost in the last slide, we'll come to this again, a penultimate slide. Now, here are just some passing remarks on a related work. Papa's U have constructed a special group scheme on A10 in mixed characteristic case for G quasi-split. The construction itself follows from Bruhat-Tits section 3.9.4, since the lattice M is not hard to construct. The main thrust of theorem 4.1 of their paper lies in proving the group scheme to be affine in the split case. And this is an important theorem in their paper. In our framework, this corresponds to the type 1 case of boldface F chosen as the pair F subscript 0 and F subscript theta, where F0 is the constant function 0 on phi bar, and F theta is of type 1. So F0 is a very simple concave function. By the main theorem, setting boldface theta as the pair 0 theta, we recover this result. Now I want to talk of fundamental objects of proof strategy before talking of the proof strategy. The general strategy is a bootstrapping or amorçage types. The first step is to build the n-parahoric group scheme associated to a collection of points in the affine apartment AT. Recall that points in the apartment are called parabolic weights for GLN by Mehta-Seshadri, and parahoric weights for semisimple G in Balaji-Seshadri. This was published in 2015. The notion of weights bridges the algebraic theory of semi-stable torsors on smooth projective curves with the representations of Fuchsian groups in GLN and semi-simple groups, the compact parts of these groups. Unitary representations I should have written, I forgot to write. Now, I want to give an outline of ideas leading to type 1. This case is the cornerstone of our results. The ideas that have led to it have a long history. Let us retrace them. So first, I want to mention a result by Seshadri in 1967. Consider the following situation of a Galois cover P from Y to X of smooth projective curves or DVRs with Galois group capital gamma. Let V be an equivariant vector bundle on Y. Consider the subsheaf of gamma invariant sections of the sheaf push forward of V. This defines the invariant direct image functor which sends V to P lower star gamma of V, which gives an equivalence of categories between equivariant vector bundles on a ramified cover and parabolic vector bundles with rational weights. So I've written this just to familiarize you. The precise definition of parabolic vector bundles involves flags adapted to weights. It is somewhat technical, but it is completely characterized by the above equivalence of categories. For emphasis, even when weights are supposed to be real, not rational. To summarize laconically, the invariant direct image functor P lower star upper gamma goes from equivariant vector bundles to rational weight parabolic vector bundles, and this is an equivalence of categories. So this is all I need for the next slide. Everything that preceded this was just to say things for. I'll continue. So in a similar vein, on a DVR, Balaji Seshadri have shown that any parahoric group scheme arises by Weyl restriction of scalars followed by taking invariants of equivariant reductive group schemes. So here, equivariant vector bundles have been replaced by equivariant reductive group schemes, and the invariant direct image functor has been replaced by Weyl restriction of scalars followed by taking invariants. And this way we get any parahoric group scheme. We generalize this to AM. Our approach is geometric in the sense we construct objects whose automorphism groups realize or give rise to the subgroups we seek. In his work on degeneration of torsors, Balaji observed that the Lie algebra bundle of a parahoric group scheme on a DVR carries a natural parabolic vector bundle structure. With this observation as a starting point, on the open subset of height 1 prime ideals, with this as a starting point, we extend across codimension 2. In this sense, we generalize Balaji-Seshadri on curves or DVRs to ANO. Now I've been saying ANO and T, and the assumption that the maximal torus T is split and that the base ANO is smooth are crucial for us. Now I'll talk about type 2. So this construction builds on the previous one. It uses the following observations. Any non-empty closed convex bounded subset omega of the apartment A can be realized as the convex hull of a finite subset theta 1 to theta s of points. On a DVRO, the Bruhat-Tits group scheme G subscript omega is precisely the schematic closure of G cross spec K in the fiber product G theta J under the diagonal map. In other words, a bounded subset associated to a bound, we can realize it as a convex hull of some points. And then, in fact, the group scheme can be recovered from parahoric group scheme. A group scheme of type 2 can be recovered from parahoric group schemes. Using large characteristic methods, such as the Baker-Campbell-Hausdorff formula, we extend the toral and unipotent group schemes across codimension 2, preserving flatness. We set boldface theta as the S-tuple of points theta 1 to theta s. Using the work of Michel Renaud, we embed the extended cell structure as a subgroup scheme of G boldface theta, which is type 1 group scheme. We then show that the role of the crucible GLM of proposition 2.2.10 in Bruhat-Tits, which was shown to be problematic in counterexamples, can be played by G subscript theta. Thus, from an extended cell structure, so the extension of the cell structure is happening here. And the word thus refers to a generalization of this. We obtain a NPT group scheme of type 2. It is at least quasi-affine, which means we are not able to prove that it is affine. Now type 3, this case is reduced to the previous case of type 2. The main facts we use are already in Bruhat-Tits. They are, over a DVR, any concave function for a semisimple G is induced by concave functions on groups of type AN. And for AN, all concave functions are of type 2. So now here is a conclusion that I wish to draw. For split Chevalier group schemes G, the theory of weights of Balaji Mehta-Seshadri is sufficient to schematize arbitrary subgroups of GKN containing ON valued points of the maximal torus and having non-trivial intersection with the root groups URKN and of valuation bounded below uniformly, as well as to solve the extension problem over ANO. of course, in large characteristic. Now, weights, here's an interesting remark that weights are just points in the apartment. But the space of concave functions is an intersection in this vector space of the subspace F0 equals 0 with the half spaces given by the concavity condition. And the space of concave functions form a cone of dimension, the dimension of the group. So it seems remarkable that this happened. Now I'll talk a little bit about applications. We are able to construct certain universal group schemes on several spaces which are quite similar. The Docconcini-Procesi wonderful compactification of G-add and the Mumford embedding G-add bar of the relative group scheme G-add A. The loop group wonderful embedding XAF of the adjoint affine Casmoudi group GF-add constructed by Pablo Solis. So these are some applications. The group schemes we construct are sufficiently universal and behave sufficiently well under specialization to be called Bruhat-Tits and wonderful. Now consider another application. Consider a family of smooth projective curves degenerating to an irreducible nodal curve. Now consider a family of principal G bundles degenerating to the limiting curve. We are able to describe the limiting objects as limits of torsors on specializations of BT groups, two BT group schemes. In some sense, this was already done by Balaji in his previous paper. The limiting group scheme corresponds to a concave function, which is the sum of two concave functions of type 1, but itself is not of type 1, like the m theta of section 3.2.14 of Bruhat-Tits that we saw earlier. The remaining slides contain introductory comments on the construction of the group scheme in type 1. And looking back, some motley of comments to familiarize the main theorem. And some details of the paper of Papaziou. And some small remarks on higher local fields of Parshin and Carter. I'm saying this in case a member of the audience is interested. I'll stop here. Thank you.
What would be a universal group scheme over the wonderful compactification, say, of a simple adjoint group?
Yeah. So on the divisors, we assume we are given so it's very much like the ANO situation or ANK situation that the we assume we are given on the generic points of the divisors group schemes, and we are able to extend them.
So what would be the fibres?
Yes, yeah. So the fibers are that we are given the data on the generic points of the divisors. So we are given these group schemes, and these group schemes correspond to some concave functions. And now take a point, you're asking me, so I'll tell you what the fibers of diagonals are. And so diagonal, for instance, in A2K, it's the sum of the two concave functions chosen on the axis, on the two divisors. And the general case is similar. That is, it depends on trig point. We take the trivial group scheme with constant fibers. And then suppose we have prescribed Bruhat-Tits group schemes at divisors which are meeting at normal crossings. That's the situation that we are. This is the data that comes to us. The generic points of divisors, Bruhat-Tits group schemes are given to us, and we glue them with the constant group scheme. Our transition functions can lie more generally in the maximal torus. I forgot to say this. They need not necessarily be identical. Now the question is, how do we extend this? So suppose take a point where a few of the divisors meet. Let's say k of the divisors meet. Then the group scheme corresponds to the concave function, which is a sum of these the concave functions of the corresponding divisors. So here is a very interesting remark that if you go to the closed fiber and look at the root data of the closed fiber, the semi-simple group scheme, then it always corresponds to the set of roots such that fr plus f minus r is 0. So you see that this is a general result in Bruhat-Tits, that the roots that survive are those such that fr plus f minus r is equal to 0.
Okay, so you have the same kind of phenomenon there. Yeah, I see. Yeah.
No. So the interesting thing is that because you get sum of concave functions, therefore the set of roots that survive the root system can only shrink, because we have this condition that fr plus f minus r anyway has to be greater than or equals to 0.
And if it does not shrink at all, you are in the reductive case, right? Your model is going to be
semi-simple case. I am in the semi-simple case.
Yeah, yes, it will be semi-simple over the whole thing, right?
Yeah. No, so if it doesn't shrink at all, you know that on some divisors it was a trivial group scheme corresponding to the origin. That's the only way it could have happened.
Yeah. Okay. This is coherent what I remind. Thank you.
Yeah, no, but probably it's very elementary. Maybe I just say it that there's a very funny observation that mr theta plus m minus r theta can only be 0 or 1. It's a very elementary observation. It can only be, and because of our hypothesis, because r plus minus r is 0, therefore f of r plus f of minus r has to be greater than or equals to 0. So if you take sums of concave functions, the root system, as you go to deeper points, the root system can only shrink. And if it remains the same, this means that on some axis or divisor, it was the Chevalier group scheme, corresponding to origin.
Okay, maybe one other question. Okay, so I have one. Could you discuss the relation with this Parshin higher local fees, because it's ready?
Yes, that's right. Yeah, so I can discuss that. Yeah, just 1 second. Okay. So, well, the construction and the steps are long, and then this was some looking back. And now here, so in the mid-90s, there was an approach to Bruhat-Tits buildings over high dimensional local fields made by Parshin with possible motivation from questions in arithmetic. So unlike Parshin, our aim is not towards generalization of the building. Rather, we follow the general spirit of Bruhat-Tits, namely to define subgroups of GKN characterizable by group schemes over spec ON. So our starting point is different from partial. And I can say geometrically that we are treating the divisors at an equal footing. But in some sense, partition, what he's looking at geometrically can be said as follows. He's looking at a sequence of closed subschemes, one contained in the other, such that the successive one becomes a divisor for the preceding one. So, but we look at n divisors meeting at normal crossings, and our divisors are all on an equal footing.
Okay, thank you.
Yeah, just 1 second.
Yes.
So, just 1 second, sir. Yeah, so just for the simplicity of exposition, I have assumed that F0 is 0. But actually, we have generalizations of these results to Moy-Prasad group schemes as well, where F0 is not supposed to be 0. But it's the simplest generalization of congruent subgroups and parahoric group schemes, the simplest cadre.
Okay, okay. Is there